Okay, similar to the last problem, I've got a 5 kilogram block sitting on top of a 10 kilogram block. The friction between the blocks is 0.6. That's not the force of friction, but the coefficient of static friction. It'll have a lower coefficient of kinetic friction. However, we're not going to get there because our assumption is the blocks slide together. We've got no friction between the bottom block and the surface, and I'm going to find the maximum applied force. Now, if you watch the previous video, we found the maximum applied force that could be applied to the top block and determined that it was 44.1 newtons. Will it be the same when you pull on the bottom block? Is the maximum force that you can apply to the bottom block without them sliding also going to be 44.1 newtons? Well, let's check and see. Okay, so let's analyze this problem. And we'll look at the top block in isolation. We have a 5 kilogram block. Gravity's pulling it down with a force of 49 newtons, and the normal force will push back up with 49 newtons. 49 because 5 times 9.8 is 49. We have a force pulling it forward. See, we've got two blocks, one block on top of the other, and I'm pulling on the bottom block. And when I pull on the bottom block, the top block gets pulled forward. What is pulling that top block forward? Friction. If there was no friction, the top block would stay in place and slide off and fall. However, with friction, keeping it from sliding, the top block gets pulled forward. So on this free body diagram, what force is being applied forward to my top block? It is the force of friction. The force of friction is the coefficient of friction multiplied by the normal force. So it is 0.6 multiplied by 49. It is 29.4 newtons. What force is pulling back on this block? The answer is there is none. So the acceleration that this will experience if the forward force is that maximum force of friction is 29.4 newtons divided by our mass of 5 kilograms. So 30 over 5 is 6. It's going to be almost 6. It is 5.88. So the acceleration is 5.88 when we pull on it with a maximum force. Now, remember from the previous problem, we had a lower acceleration if we pull on the top block. We get a higher acceleration if we pull on the bottom block without them slipping. Now let's look at the bottom block. Our bottom block has a mass of 10 kilograms. Friction is pulling back on this block. You see, look here. We have one block on top of the other, and we're pulling the bottom block forward. So we got our hand on that bottom block, and we're pulling it forward. The top block, sitting upon it, is going to pull back when we pull forward. It has inertia to keep it in place, and there is friction here. Friction opposes motion. So as that bottom block gets pulled forward, friction will oppose it by pulling back. That friction is between these two blocks. So the force of friction, I'm just going to take from my previous case here, whereas friction was pulling the top block forward, that same friction pulls the bottom block back, 29.4 newtons. So I've got 29.4 newtons pulling me back. I've got an applied force pulling it forward. We've got gravity of 98. We have a top block pushing down with 49, and the normal force will push up with 147. This vertical components of force is the same as the previous question. What is our net force? Our net force is what's left over when all these forces cancel each other out. Our net force is the applied force minus the force of friction in this case. So it is my unknown applied force minus 29.4. I went through this part rather quickly. Our assumption is that our block sits at rest. So the upward and downward forces cancel one another out. Gravity's pulling down on the block. That's my 98. The top block that sits upon it is pushing down on it. That's my 49. However, since this system is neither accelerating upward nor downward, the net vertical component of our forces is 0. So the normal force, that's the force of the surface, the table pushing back up on it, is going to be 147, which is what you get when you add these two together, so it cancels them out. Friction's pulling back, and our applied force is pulling forward. The applied force is greater than friction, allowing the system to accelerate forward. So that applied force minus friction is our net force. What is our net force? Well, the system moves together. And for this system to move together, the acceleration of the top and bottom block has to be identical. The acceleration of the top block is 5.88, ergo, so is this one. So our acceleration is 5.88 meters per second squared forward. And with that forward acceleration, we're going to have a net force, F net equals ma. We're going to have a net force of this acceleration multiplied by this mass. So 5.88 times our mass of 10. So it is 58.8 newtons. So I've got 58.8 newtons as a net force pulling this forward. I'm going to get rid of that minus 29.4 by adding it to both sides. So the maximum applied force that can be pulled on the bottom block is 88.2 newtons. So consider this in conjunction with the previous video. If you have a system with a smaller block on a larger block, and you're going to apply a force to one, or you're going to apply a force to the other, you can apply a greater force to the bottom block in this case, where the bottom block has a greater mass. You can apply a greater force to it than you can to the top block, such that they move together without them sliding, without this block sliding off of that one. I think your intuition would probably tell you that if you were looking at a stack of boxes, like, well, this is my setup here to hold my camera, hold my phone on so I can make this video for you. And I think it's rather clear from our intuition that I could push on this with a greater force than I could push on this and allow them to move together. Now, that's not a perfect experiment to verify these theoretical results, because in this situation we simplified it and had no friction. We had no friction between the bottom block and the ground. And that's not what this is demonstrating here. So you have to be careful and not over-assume what it is that you've found.